Let's do an example using phasors. Here's a circuit. Looks very similar to circuits we studied when we were talking about information circuits. The only difference here is now V of n is of a sinusoidal form and has a fixed frequency. In this case, we've chosen this example has a frequency of 60 hertz, which gives us an omega of 377 radians per second. So let's go ahead and write the values in on the circuit. And now we need to solve the circuit. We're going to use a procedure similar to what we used when we were dealing with information circuits, except for, again, now it's going to be a bit easier because we have a single frequency omega. So let me just start by writing the time version, 155 cosine 377t volts. Let's write it as a phasor, which will be 155 at an angle of 0 degrees. Again, the units are volts. So to solve the circuit, we could use any of the techniques we've used before. In this case, we have only we would only need to write one nodal equation because this node's very trivial. This is just the voltage 155 at an angle of 0. So I'm just going to choose to write nodal analysis equations. So I will have V of t minus this voltage over this resistor plus V of t minus 0 over this complex impedance plus V of t minus 0 over this complex impedance. So as we go, the first thing we need to know is what is omega. And omega is going to be, in this case, 377 radians per second. So just like I wrote before, we can write the voltage source as a phasor. So Vn will be equal to 155 at an angle of 0 degrees. And usually I do put in the symbol for degrees, and the unit is volts. So writing KCL equations, if we call this node right here V, we would have V minus 155 at an angle of 0 divided by that resistance, 1/2, plus V minus 0 over the complex impedance, which will be, remember that the complex impedance of an inductor, CL, will be J omega L. Okay, so in this case, we'll have 2, the resistance, plus J omega, and L is 1/10. And then the next branch will have V over 2/10 of an ohm plus J omega L, which is J omega 2 over 100. So the value of omega actually gets plugged directly in. So now instead of having to write everything in terms of S, we have an equation that has just numbers. They're complex numbers, but they are simply numbers. So all you have to do is put them in your calculator and solve. So when we solve for V, we end up with 154.1359 at an angle of 4.5339 degrees. Okay, one of the things you need to remember here is to carry as many digits of precision as possible in your calculator so that your rounding does not give you errors. Now, let's go back and look at that again. So what I'm going to do here is notice each of these terms has a V in it. This is a very simple problem. Okay, and so we're just going to factor out that V and solve. And when we do that, we end up with V times this number is equal to 310. And so just plug all these things in your calculator or MATLAB or whatever you're using to do your computations and solve. Here is how we would write it with MATLAB, just to give you a little bit of, as a reference. V is equal to 310 divided by, and then just make sure you put the proper parentheses in. You can use J or I with MATLAB. I usually use J when I type it in, and I read I when I read it out, and that's fine. So you solve, you get this value for V. You'll need to write it in phasor notation, so you have to use the ABS function to get the magnitude, and use the angle function to get the angle. Now the angle will be in radians, so we want to convert it to degrees, so we multiply by 180 divided by pi. okay? So we can also solve for the currents I1 and I2 by taking that voltage and dividing it by the complex impedance. And again, we solve. The last thing you have to do is write it in time form, and I will ask you to write everything in time form. First thing you notice is that in all cases, omega is 377t because it doesn't change. And in each case, we would just write V of t is equal to the magnitude of that phasor, cosine 377t plus the angle of that phasor. Make sure you get the right units.